Good morning. Today we will start to concentrate on helicopter stability. First, remember, what is the stability of a free uncontrolled aircraft? First, stability is concerned with the tendency of an aircraft to return or to depart from its trim condition once it is perturbed. If you remember, at the fixed-wing aircraft we used two different subsets. We described the longitudinal motion composed of the horizontal velocity or the surge U, the heave velocity W, and the pitch rate Q, and the lateral directional motion involving sway V, roll rate P, and yaw R. In general, this uncoupled behavior, longitudinal lateral, is not true for helicopter. Also, if you remember, one can treat the stability and the dynamic, the static stability and the dynamic stability. If you remember, an aircraft is statically stable if it will tend to return toward its trim condition following any external disturbance, and an aircraft is statically stable, but it can be dynamically unstable because returning to its original condition, it can oscillate back and forth around the trim condition with an even increasing amplitude. If you remember also, you studied the aircraft static stability and you learned that if you give a positive disturbance in angle of attack, a nose up, it will produce a nose down negative pitching moment. So the variation of the pitch moment with respect to the angle of attack had to be smaller than 0 in order that the aircraft to be statically stable. So you have a nose down negative pitching moment. For helicopter static stability, we have the so-called speed stability. Namely, if we give an unintended increase in the speed, generally the rotor will flap back and then it will produce a nose-up pitching moment, so it will have a stabilizing effect. Therefore, we define the derivative mw, so the variation of the pitch moment after a perturbation in heave velocity, and we say that the rotor actually rotor is stabilizing, and we have a positive stability because if left alone the helicopter will pitch up and then will slow down to its original trim speed. The statically unstable condition corresponds to this derivative smaller than 0 because the helicopter will pitch down and it will increase its original trim condition after a positive after an initial perturbation positive. For helicopters, we can have a destabilizing effect of the rotor downwash, which acts on the horizontal stabilizer. You see here two pictures. Imagine that I am in an initial condition with a helicopter. So you have the rotor downwash from the main rotor acting on the horizontal stabilizer. And imagine that we are going to give a perturbation, so we are going to fly 10 knots faster. What will happen is that as the speed is increased, the downwash behind the rotor, it will decrease. In this way, the angle of attack at the level of the stabilizer will increase. This will create a higher stabilizer lift, which will have actually a destabilizing effect on the helicopter. And then it can be this destabilizing effect, so nose up, it can be even bigger than the stabilizing effect coming from the rotor, which damps always the motion. Also, remember that the center of gravity position is very important for the static stability. Generally, a front 4 CG is stabilizing, while an aft CG is destabilizing. Why? For example, if you have on the left hand side, you fly forward, so level with 1G flight. If you encounter an up ghost, increased rotor thrust will produce a nose down moment about the CG. While if your CG is behind the rotor, if you have an increased rotor thrust, it will produce an even destabilizing nose up moment about the CG. For the dynamic stability, let's consider now the longitudinal motion. Here, we assume that we start from the nonlinear equations of motions that we have derived in the 3 degrees of freedom helicopter model. So, the u dot, w dot, q dot, and the theta f dot equations. Assume small perturbation around the trim condition in u0 plus delta u, theta f plus delta f, and so forth, and also assume perturbation in the control variables, which are in our longitudinal model, the collective and the longitudinal cyclic. In this way, one can calculate the perturbation in the forces delta x, delta z, and delta m, and having these forces and moments, one can represent the perturb system. If you remember, the linearized mathematical model that you have derived, it involves the stability derivatives in a x direction, z direction, and the pitch moment. And these are the control derivatives, collective pitch and the cyclic pitch. In this way, we can do exactly like the fixed wing, linearize the helicopter nonlinear model and arrive to a linearized mathematical model. You also remember that for the stability of the 3 uncontrolled helicopter motion, we have the linear differential equation x dot equals with ax. So the A is reproducing the natural behavior of the aircraft, and you arrive at an eigenvalue problem that you can solve. You have a characteristic equation, and then representing the solutions of this equation, one can obtain the eigen values of the motion. Also, you see that if you have an oscillatory motion, one can have a divergent mode if the real part of this value, so the A, is higher than 0, and one can define the time to double the motion, and you have an oscillatory mode if this real time of mode it is smaller than 0, and one can define in this case for an oscillatory mode the time to halve the motion and the period of the motion. Now, these all have been, and remember also that there is a correlation between the complex plane and the system natural response. If you would represent the real part of the solution and the imaginary part of the solution, you would be that on the right hand side the damping is higher than 0, so it is undamped and the motion will increase. In this case it will be oscillatory, and here on the real axis will be non-oscillatory, and the motion it will be unstable, while if we are in the left hand side of the complex plane we have an stable motion and the oscillation will be damped. Now, if you remembered all this, let's try to see how it looks, the phugoid mode, in the case of a helicopter. In longitudinal stability, one can define the so-called phugoid mode, which is an exchange of energy between the speed and altitude. In the approximation, if you have the helicopter in a level flight, if you give a vertical thrust, it will build the phugoid mode as an exchange between the pitch and the horizontal velocity. The heave velocity W, it has usually a smaller contribution to this mode, so smaller than 10%, and it can be assumed 0. Therefore, in a phugoid approximation, one can consider that the phugoid is a combination of the surge velocity, U, and the pitch moment. And the helicopter will start first speeding up, slowing down, speeding up, and so forth. The phugoid mode in a helicopter, it is usually an unstable mode. So if you represent this system of equation and you can solve the characteristic equation, the phugoid will be an oscillatory mode, and usually the derivative mu, it will make the mode unstable. So the variation of the pitch moment when the surge velocity is changing. Actually, in hover, the phugoid mode seems a kind of swinging pendulum. So helicopter is like a swinging pendulum while it's hovering. Because the phugoid mode, it is unstable, one needs to define a stability map for a helicopter. Usually, to damp the phugoid mode, so to stabilize the mode, we have to add a horizontal stabilizer. In this picture, you see on the horizontal axis the angle of attack stability. The positive angle of attack stability means a nose-down pitching moment as the speed is increasing. On the vertical axis, you see the speed stability. A positive speed stability means a nose-up pitching moment as the speed increases. You see that for a helicopter, usually we have regions of unstable behavior where the phugoid is unstable. Here is a helicopter without horizontal stabilizer. If we add horizontal stabilizer, we will go into the stable region. However, be careful. Changing the stabilizer incidence, it can increase or it can decrease the stability of the aircraft. So it will move up, it decrease the stabilizer incidence, it will move down, increase the stabilizer incidence. Therefore, we have to deal with this phugoid mode in a helicopter, especially for the hovering, which is unstable, and try to make the aircraft stable. Then another mode which characterizes the longitudinal stability of a helicopter is the short period. If you are in a level flight and there is a vertical gust giving, the first response, it will be the short period mode, and it will be a slowing down of this motion. Why? Because, as I said, the flapping motion is usually stabilizing the helicopter motion. Usually, the surge velocity u contributes to this mode with less than 10%, so it can be assumed 0. Therefore, if you consider the heave and the pitch equation, you can find out the eigenvalues of the short period mode. The short period is a damped motion, and you can use this equation for finding out the short period mode characteristics. In hover, the MW derivative is very small and can be neglected. This can lead to actually to uncouple real modes for pitch and for heave. In forward flight, the MW will couple the pitch and the heave motion, and there will be a resultant stability depending on the sign of this derivative. Therefore, you learn that aircraft, the short period is usually an oscillatory mode. You will see that actually in helicopters, especially in hover, this mode it is non-oscillatory. So, concluding, longitudinal stability of a helicopter, it means that we are having a helicopter disturbed from a forward flight condition by a vertical gust. So it is made up of a short period incidence adjustment followed by a long period usually unstable oscillations at a constant incidence. This ends this part on longitudinal stability. So the short period and the phugoid mode.